As we start the last chapter of the AP course, we're working with chi-squared tests over the next two sections. Today we are going to focus in specifically on the goodness of fit test is what we're going to do. I'm going to talk about the other two types of tests that will be in tomorrow's lesson. And then on Monday, we'll finish up with the last section, which is testing for slope and linear regression, a hypothesis test. So today, again, as we look at a chi-square test for categorical data, if you think about it, a lot of the stuff we've been doing like in the last unit that we just took a test on, we were dealing with quantitative data is what we were dealing with. We were using the mean and the standard deviation, which means we had quantitative data that we were get to add up and do stuff and find the means and the stuff of it. The other version of categorical data that we did hypothesis testing with was back with proportions. That was categorical data. The difference is when we were dealing in that chapter, we were dealing with typically just one category. We may have compared two different groups, but it was really just one thing we were looking at and we were using a percentage about. And so now, when we have multiple categories, we can't use the testing procedures from the proportions hypothesis testing to do this stuff. That's where the chi-squared comes into play. There's also another one that deals with multiple variables, which is ANOVA, is a type of testing and that you see out there. It's not on the AP exam, so we don't get in there. Your calculator actually does the ANOVA test. It does one out there. And that's where some of you, kind of you being one, if you're going to pursue stuff in medicine, you will probably get into more ANOVA testing later on in some of your courses as you do things because of the multiple variables and those things and as they're trying to analyze stuff. So that would be, I know my daughter and son-in-law with the pharmacy, they did more ANOVA testing is what they would do with their data in the research phase. It would end up happening. So, but I haven't had to dabble in it that much. I'm a very novice person on when it talks about ANOVA testing. Why do we have another type of significant testing? Well, again, here it is as I come back to write it, and even though I just said it at the front of the room. One sample Z significant test only analyze the proportion for one category. That's all they do, just one category. One category. Two sample Z significant tests only analyze the difference in proportions. The difference in proportions for one category. Now, what if we want to analyze proportions for all categories or more than one? Okay, so when we think about it, all categories or more than one categories, what can we go through and do? More than one. Sorry. It's a crazy than one. Sorry. Man, I don't know why my pen acts up so crazy. With that in mind, that's where the chi-squared comes into play. And we have three different types of chi-squared testing that's out there. We have a chi-squared goodness of fit. This test takes one variable and analyzes its distribution among all the categories. It compares the expected distribution to the actual. And by comparing those two, we're trying to determine if there is a difference in the distributions between the expected and the actual. For this test, we compare counts, not proportions. We actually look at the counts, not the percent of each little part. We actually look at the total count of the expected versus the actual as we do things. A chi-squared test for homogeneity. We analyze distributions, but now we are checking if the distributions is the same or different. Is the same or different. Again, this is going to be more tomorrow's lesson for several populations or treatments. The third type of chi-square test is for association or independence. For this test, we sample or experiment from a single population and break them up among multiple variables. We then check to see if there's an association, is it not independent between those variables. And again, as I mentioned earlier, these things are the same test. They're the same mathematical calculation test that we're doing here. The main difference comes from the following. When you're doing a chi-square test for homogeneity, you take two samples. When you're doing the chi-square test for association or independence, it's one sample. It's a one single sample. And that dictates, as you read the problem, is what we decide, well, which am I going to do? And so forth. So, again, we'll get into that more specific tomorrow and give some examples of, hey, this is why this one's for homogeneity, why this one is for association or independence. When we look at a chi-squared distribution, this distribution is a measure of distance of the observed count from the expected count. Unlike a normal distribution or a t-distribution, a chi-squared distribution is not symmetrical. It is not symmetrical. The chi-squared distribution does change based on the number of categories. Notice we didn't say sample size. It says categories. The number of categories creating. And this creates our degrees of freedom. And again, if you want to make a little note down here, degrees of freedom is equal to the number of categories. Now, in case and a number of categories, and then it's minus some number. There are times when we're going to be subtracting 1. There's some times we're going to be subtracting 2. So that's why I have a generic number pound symbol there, a number sign there, because it's not like the degrees of freedom when we did a t-distribution when we just subtracted 1 from our sample size. Now, some of this types of testing, there's different ways to come up with degrees of freedom. On the homogeneity and the association, one of those involves multiplying and stuff, multiplying this times this. And so that's where, when we look at today's stuff, we are subtracting a number, but one of the other testing for chi-squared, you actually multiply two numbers together to get the degrees of freedom and stuff. So it's a little different. So be careful is what I'm trying to say is it's not the standard default subtract 1. Subtract 1 all the time. Okay? So here's an example, or here's what they show what the chi-squared graph looks like based on a degrees of freedom of 1. And as the degrees of freedom increase, notice with the degrees of freedom of 1, it looks almost like an exponential decay graph. Okay, sloping down to the left, to the right is what it looks like. Again, very skewed. Even with the degrees of freedom of 4, I'm still skewed right. Even the degrees of freedom, I'm still skewed right on the degrees of freedom of 8. So as we look at it, the distribution is a measure of the distance of the observed count from the expected count. Let's see, as you can see, here we go. It is a right skewed, find my note spot. It is a right skewed graph. All chi-squareds are this way. They're right skewed. And again, they only have positive values with only positive values. So we have nothing on the negative side, which means if we get something negative, we probably did something wrong if we're doing the chi-squared. Okay, so just keep that in mind. Okay. As degrees of freedom become larger, it becomes less skewed. As degrees of freedom become larger, larger values become more probable. So a higher p-value. More probable. The mode or the peak is going to be at the degrees of freedom minus 2. So if we look at our example here of the tealish graph that I see there, we have a degrees of freedom of 8. 8 minus 2 is 6. And if I look on this graph, notice where the peak of that curve is. There's my mode for that graph there. So no matter what you're doing, and again, if we think about the degrees of freedom of 4, 4 minus 2 is 2. On the orange graph, the peak happens to be there as well. Okay, so the peak or the mode of a chi-squared graph is going to be whatever the degrees of freedom minus 2, that's where that value is going to be. The mean will be the same as the degrees of freedom. It will be the same. So whatever the degrees of freedom are, we are. So whatever symbol we're doing. So we really don't talk about it. What it is a mu sub x squared. The mean of chi-squared, that's equal to the degrees of freedom. Usually don't see it that much. Chi-squared. Again, basically, it looks like an X, but again, it's not really two diagonal lines. It's like one diagonal line, the other one's kind of a little curvy, and then you put the squared up there. And it's really easy for us to mistake because we just think about X squared as just a normal X. So the line coming back from the left to right is what's curvy. The variance, what will the variance be? The variance is 2 times your degrees of freedom. 2 times your degrees of freedom. Now, how do we calculate the chi-squared statistic? Remember, we've had a z statistic. That we just did in the last unit. We had or t statistic is what we did the last unit, sorry. Z statistic was the previous unit. So now we have a chi-square statistic. How is that calculated by hand? And we have to use this on the free response. We do have to show some of these things. It is the sum. So when we look at the summation symbol, the sum, and it's the sum of a certain fraction. On the top of the fraction, it is the observed value minus the expected value, that quantity squared, and we divide it by the expected value. Again, we're going to get practice doing this in a moment. So it is more or less adding up a bunch of fractions together, and that becomes your chi-square statistic. It's how you come about getting it. We can use the calculator, but again, as we progress through, if you need to find the p-value, if you like doing the p-value associated this, we would use I always like to do like vertical line that way first. We do a chi-squared CDF. We use a chi-squared CDF to help us determine our p-value. Now, we can use the chi-squared testing in there. The challenge is there are 2 tests inside of the calculator, and you have to be very careful. You just don't want to use the one that just says chi-squared, all right? Because actually, for today's lesson, we're doing the one that says, I think it says it has the chi-squared symbol, and it says GOF is what it says. So that's the goodness of fit. Okay, whereas tomorrow's lesson, we're using the other chi-squared feature. Okay, so you got to be really careful what you're clicking on when you get ready to use the calculator feature, if you're using that to get your stuff. All right, now, conditions for a chi-squared test. We always have these things. First, always got to be a simple random sample. or a randomized experiment. Now, here's where the large sample changes. For chi-squared, all expected values, not observed, but expected values. All expected values are greater than or equal to 5. And in this case, it's okay if the expected counts are decimals. And then for the independent piece, this goes back to being the same thing. Do we have 10 times our sample size? Is it less than the population? And if so, then we are independent. Okay. So as we go to write our chi-squared test, we're in the state phase. We want to explain what we're going to do. We want to perform a chi-squared test. In this case, for today, we're doing goodness of fit. If you just say chi-squared test, you lose a point there. You got to specify which test you're using, in your statement there. You just can't just say chi-squared. You got to say, is it goodness of fit? Is it the association? Is it the homogeneity? You have to use those things there to specify which one you're doing. If you say association and they had down there independence, they'd be fine. Okay, that's the only one where it'd be okay if you miswrite association or independence. You just got to make sure it's one of the two. In our null hypothesis, we're putting what are the expected proportions based on the population. We must list all of them. So, for example, I do have the data from the M&Ms that we can do here in a little bit after a couple of these from today from my other class on what proportion one does Hershey's claim, or whoever makes M&Ms, is it Mars? I think it's Mars, that M&Ms makes. They say that there's a certain percent of each color inside the bag. And so our null hypothesis would be, is that true? Are those proportions true? In our alternative hypothesis, we're just going to say that we don't have to use it greater than, we don't have to use it less than, we don't have to use it not equal to symbol. We actually say at least two of those proportions are incorrect that are stated in the above process in the first part, okay, in the null hypothesis. Because again, if we have certain, like if we think about the M&Ms, all the colors percentages should add up to be what as a total theoretically? 100%? Because if there's 5 colors, we know they're not all 20%, they're different amounts, but that all together should add up to be 100%. Because there's no other mysterious color in the bag of M&Ms normally. And so, with that in mind, if one of the colors is not correct, that means there's got to be another one not correct. At least another one. So there's got to be at least 2 that are not what they're stating. All right. So, that's a nice generic statement that we get to write here. At least one or at least 2. You can say either one of those 2 things is incorrect. We have to decide. We have to define what each of the P's are, especially if we're using symbols. If we said P sub red, P sub blue, we would say that's the proportion of M&Ms that are color red, and we'd have to do that for each one. So it gets pretty lengthy in the statement phase for a chi-squared test for goodness of fit as you write it out for the stuff there. We're gonna do a chi-squared test for goodness of fit if conditions are met, our random, our expected counts, and then we also go through the observations are independent or 10% rule. In the do phase, again, if we're doing it by hand, we get our chi-square statistic by doing the sum of the observed minus the expected divided by the expected. Now, again, we know we have multiple choice answer questions that we do deal with. And with that in mind, sometimes we have to pick the right setup for those things where they show the fractions being added together, and we want to make sure it's the numerator squared, but it's observed minus expected over expected. We don't want to see the observed number twice. We want to see the expected number twice. is what we want to see in each of the fraction as we go forward. That gives us our chi-squared. Calculate the p-value using a chi-squared CDF with the lower bound and upper bound and degrees of freedom. Remember, degrees of freedom is categories -1 is what we're doing for this, for doing goodness of fit. Now, is our chi-squared statistic, is it going to be a less than, greater than, or not equal to? Oh, sorry, my bad. Is it the lower bound or upper bound? That's what I meant to say. What do you think? If we're right skewed, then it's, to me, it's going to be primarily, most of the time, should be the lower bound is what it should be each time. So remember, p-value is the probability of getting the chi-square statistic if the null hypothesis is true. Remember, we compare the p-value to the alpha, whatever, to the significance level, whatever it is, using the same ones that we do, significance level. If the p-value is less, we reject the null hypothesis. If it is not less, we fail to reject the null hypothesis. And again, as we write our conclusions, like we've been practicing for a couple chapters now, we reject the null hypothesis, so we do have convincing evidence to support the claim of the alternative hypothesis that at least one of these proportions is incorrect, is pretty much what we're saying. If we fail to reject, we do not have convincing evidence to support the claim that at least one of these proportions is incorrect. Okay, because again, that's pretty much how it's going to be, is that at least one of the proportions is incorrect or is correct, so, or so forth. So here's our example. And again, we've done so many things as we're doing it. I think we jump straight into the next page is where we actually do the actual hypothesis testing. So we don't have to write a lot of it on the first page, but this is where I had it. According to the 2000 census of all U.S. residents aged 20 and older, 19.1% are in their 20s, 21.5% are in their 30s, 21.1% are in their 40s, 15.5% are in the 50s, 22.8% are 60 and older. The table below shows the age distribution of a sample of U.S. residents aged 20 and older. Members of the samples were chosen by random dialing a landline telephone numbers. Fantastic. So there's my table. They ask us, do these data provide convincing evidence that the age distribution of the people who answer landlines telephone surveys is not the same as the age distribution for all U.S. residents? So again, here are my categories. All right, so that's going to help me on my degrees of freedom. So when we think about it, these, my categories here is I have 20-year-olds, 30, 40, 50, 60-year-olds. There's 5 categories here. So our degrees of freedom is going to be 5 minus 1, which is 4. So eventually when I need a degrees of freedom, I take up, hey, I have 5 different categories, subtract 1 from it. There is my degrees of freedom, 4. So when we need that, we have it already done for us. Now, in our statement phase, we will perform a chi-squared goodness of fit test at the, again, we're going to go ahead and do 5%, so 0.05 significance level. In our null hypothesis, we're going to go through and write that each one of those, P2, 3, 4, 5, and 6, and then we have to define what those are. And they went through and defined what they are here in a second here. So going back to our data, they said 19.1% of them were in their 20s. And then it was, I'm going to zoom in. I got it written on a piece of paper. 0.215 was the next one. Then it was 0.211, 21.1% was in their 40s. 15.5, so 0.155, and then it was 0.228. So there's the proportion in each of the categories. Again, in our alternative hypothesis statement, we're going to say at least one of those is incorrect. You can also say at least two, but you can just say one. We do need to define what they are, so they chose a nice generic route where P sub I is equal to the true proportion in their 20s, 30s, 40s, 50s, and 60s and over age group. Now, if you want to do each one separate, you can. It's just going to take you a long time. If you go through and say that P sub 2 is equal to the proportion of blah, blah, blah in their 20s. All right, so it could take, or you could say they're between 20 and 29. It could take a while to do that stage. So this is a nice little shorter way when we have a lot of categories there is to use some little script there to make it go a little bit quicker. Again, we are going to, our plan is to do a check conditions and do a chi-squared goodness of fit test. So I would probably at this stage spell out goodness of fit. In the do stage, we can use that brief goodness of fit test. So random. They do say in the last statement on the previous page, members were chosen by randomly dialing landline telephones. So they do tell us there that we have a simple random sample, an SRS of 1,048 U.S. residents. They do tell us that. Now, for the normal, the large or normal condition, I guess it's really large because we're not normal because we're going to be okay. Sorry, it's medical city in my life between my mother-in-law getting the heart cath and having a stent put in, my daughter having the baby, and then my dad just said that he's going to get a pacemaker. So it's just like all over the place for our family. So large count. Here's the hard part. On the large count, we got to take each of those percentages, 0.191, and multiply it by 1,048 to get our expected. Because each of our expected need to be greater than 5. So this is where it takes a while. The more categories this thing has, the longer it takes to do this phase here. And yes, you got to do all these. If you don't, you lose total credit for that part there. So I got to check all 5 of those percentages times 1,048. Are those numbers greater than or equal to 5? So Mr. Stevens is trying to keep track of where he's at. And then the last one, 0.228. All right, so I got those primed there. Again, I went ahead and did the math to speed things up on here. The first one works out to be 200.168. Again, it's okay to put decimals there, so go ahead and leave it. Then we got 225.32. Then the next one, the next category would be 221.128. And then we have 162.44. And then the last one is 238.944, and that's greater than or equal to 5. All right, so there's all my expected counts. Now we need to use those again later on, so that's why it's okay. Hey, we did this. Now I'm going to show you a faster way to get those numbers with the calculator here as we're doing things. I'll show you some ways to do it too, besides just typing in. I'll show you how we can do something that actually gives us what we have there. And that way you can go back and fill it in later, and just to make sure that they're bigger than 5. So we are large enough, independent. We think about, all right, 10 times 1,048 is 10,000. Let's see, 10,480. So I would say on this one, reasonable to assume more than 10,480 U.S. residents. And then now I'm ready for the do stage. So to find our chi-squared statistic, again, we said it was the sum of the observed value minus the expected, that quantity squared, divided by the expected. So this is what it would look like. In our table, for the 20-year-olds, it said 141 people were observed. So 141 minus, we expected it to be 200.168. That's squared divided by 200 and then 0.168. I have to add to that now the next group of people. So the 30-year-olds was 186. So 186 minus the expected for 30-year-olds was 225.32. That quantity squared over 225.32 plus. Now I would continue doing what I'm doing here. Now, on the AP exam, you don't have to show all 5 of those fractions. You at least have to get it started, and then you can say plus and do dot, 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 and then finish up with the last one. The last category was the 60-year-olds and over, so 286 minus 235.944 squared over 235.944. Again, you do not have to show all of the fractions, but you do have to show some. And so showing the first couple plus dot, 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 then showing the last one is enough to show the reader that, hey, I'm going to do this for every single one of those observed values. I'm going to do this process, and I'm going to add up all those answers, all right, for showing work. Besides the fact, that's how some of our multiple choice questions are done. They actually have that listed, hey, which is dually right process and stuff as we're doing it. So it gives us practice being able to answer the multiple choice is what that also gives us practice of. Now we can do this on the calculator to kind of speed things up. So I'm going to grab the calculator. I'm not going to do the chi-square goodness of fit test. I'm actually going to use our tables. So I'm going to go in there, get a table. And what I'm going to do in L1, is I'm going to type in the expected, or the observed, 141, 186, 224, 221, 211, 211, and 286. And then in the next column, I'm gonna take the decimals that we found for the expected, 200.168, 225.32, and then we go 221.128, 162.44, And the last one is 235.944. So I'm going to go ahead and put them in L1 and L2. And then I'm going to tell the calculator to do the fraction for each one of those things, is what I'm going to go through and do. Okay? Alex, you can try. Okay. I was just making sure. I didn't know if it had died and so forth. So just want to make sure. So now what I'm going to do is I'm going to go up to the column header and I'm going to create a fraction. So alpha x. And on top, parenthesis, I'm going to tell it to do L1, so second one, minus L2. I'm going to close the parenthesis and then square it. There's my numerator. On the bottom, I'm going to put in L2. So I'm going to tell it in that third column to go ahead and do that fraction for me to speed things up so I don't have to type them in all the time and stuff. So now that I know I have it right, I'm going to hit enter. It gives me all the data there. So that's the answer to each one of those fractions. So each one of those fractions, and I'm just going to write it down. Don't write these down. I get this fraction worked out to be 17.49. This fraction is 6.8616. The next fraction, we don't have it written, but that's okay, is 0.0373. The fourth fraction was 14.517, and the fifth fraction was 10.619. Now, we can add all those up, or we can do a one-var stat, and it can add it all up for us. If I do stat, go over to calculate, do a one-var stat, and do column 3, I want to look at the line that has the sigma x line. That is the sum of the x values, the sum of the values in that column. Well, the sum of the values in that column is 49.5246. That is my chi-square statistic. So that's my chi-squared. So as I get rid of my calculator so I can have more room here. So my chi-squared statistic is 49.5246. Now I'm ready to find the p-value. So what is the probability that my chi-squared statistic is greater than that number there? Did anybody else get 49.5246? Did anybody get something different? Just making sure I didn't have happy fingers. Did anybody else get that number? Okay. You all stayed silent, so I'm assuming you did. Okay. So I'm going to do a chi-squared CDF. My lower bound is 49.5246. My upper bound is something really big. And then now I have to put my degrees of freedom. Well, again, our degrees of freedom we found already. It was our categories minus 1, which happened to be 4. And so I'm ready to go to a chi-squared CDF. So second VARS chi-squared CDF is option number 8. Again, my lower bound is my chi-squared statistic. My upper bound is something really big. Again, 100 wouldn't cut it in this case. My degrees of freedom are 4. Hit enter a couple times. And we find out that our p-value is 4.5379 times 10 to the negative 10. So that's 9 zeros and then 45379. So is that less than 5% or that bigger than 5%? Yeah, it's less than. Thank you for answering that quicker than my last class. So since our p-value is less than 0.05, and again, we usually write that since our p-value of, and we say what the numbers are, is, and we use the symbols, we reject the null hypothesis. We do have convincing evidence that at least one of the proportions for people in their 20s, 30s, 40s, 50s, and 60s answering landline telephone surveys is not the same as the age distribution of the U.S. residents. That's what we have. We have evidence. Now, they always ask us little sidebar questions. If we reject the null hypothesis, we can perform some follow-up to determine where the difference are occurring. Which category shows the largest deviation? And sometimes they'll phrase it in the standpoint of which category had contributed the most to the chi-square statistic. So which one had the biggest contribution to that overall value of 49? So when we look at what Mr. Stevens wrote down as the total for each fraction, which one of those fractions had the biggest answer when it was all said and done? Looking at what I have listed there, we had 17.49, 6.8, 0.03, something else, and then we had like a 14, then we had a 10. So which one of those had the biggest value? Yeah, the 20-year-olds, the 17. Okay, so that would be the 20-year-olds had the largest contribution to our chi-squared statistics. So in our case here, up here, we would say this first category, the 20-year-olds, had the biggest contribution. Now, individual terms or calculations that contribute to the chi-square statistics when using the goodness of fifth test on your calculator. We're going to do this in a second. These values are stored in this little feature right there. I'm going to show you what it looks like. When calculating using list, there will be individual values in list 3, which is what we did. Okay, remember when we look at hopefully it didn't reset it yet. When we look at our lists, there's our list, and if we zoomed in on L3, we could see that 17.49, that top one, had the biggest one there. So if you're choosing that way to get your stuff, it's you can see that column there. Which was the next age group that had the next biggest contributing factor? Looks like the 50-year-olds, right? The next to last to the bottom, because the 60-year-olds were the last one. So right up above it was the 50-year-olds, so my age group. They had one. Now, when you look at it, the 20-year-olds was a lot higher, expected actual. The 20-year-olds had a lot lower observation of what actually, so forth, compared to what they were expecting. Whereas the other way, the 50-year-olds, it was a lot higher than what they were expecting in that standpoint. So, when completing a follow-up, talk about the size and direction. The size and direction of the components of the expected value. So that was what I was kind of doing right now with, saying that, hey, it was a lot lower than, like the 50-year-olds were a lot smaller than what they were expecting because, looking at the two parts. All right, another problem. Let's go into this one, and this one we'll do on the calculator. I believe I have it set up my notes for us to do it that way. So we'll examine the control, the C and B, that part there, to show you where the expected values are in that one, and so forth. So the last example, again, is a nice short day today, is what it was, even though it's 11:05. Not that short. In his book, Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically, since January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from. Players born in January will be competing against players up to 12 months younger than them. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time, more coaching, and have a better chance of being successful. To see if this is true, a random sample of 80 NHL players from 2009 to the 2009-10 season were selected, and their birth days were recorded. Overall, 32 were born in the first quarter, 20 in the second, 16 in the third, 12 in the fourth. Do these data provide convincing evidence that the birthdays of NHL players are not uniformly distributed throughout the year? Okay, so that's what they're saying, that it's not uniformly distributed. We will perform a chi-squared goodness of fit test at a 0.05 significance level. And most common one is that, so that's what we're going to use. Now, our null hypothesis. When we look at it, we're testing to see that it's not uniformly, so if it was uniformly distributed, there's 4 quarters in a year, so that would mean that it would be like the proportions would be 25% for each quarter. If it was uniformly distributed, it would be 25% for each one. So that's our null hypothesis. Our alternative hypothesis, at least one of those is incorrect. And then we define what the P sub I is. It's the proportion of birthdays of NHL players in each quarter, where 1 is from January to March, 2 is from April through June, and blah, blah, blah. So, again, I would again state in here, a chi-squared, and again, you can use the symbol chi-squared goodness of fit test. All right, if conditions are met, I would rather you all get in a habit of writing that in every time. That way, it's there and we don't lose points for it. If conditions are met. So now, when we look at random, they said they did a simple random sample of 80 NHL players in the 2009-2010 season. Our large sample, this is where we do our expected counts. Our expected, again, there is our expected was 25% for each one. And it was 80 people was our sample size. And that would give me 20. We're expecting that it was evenly or uniformly distributed, so everybody was the same. Again, those are all greater than or equal to 5. So we do meet the large count condition. Independent. Now, here's where we got to be careful. What I would say here is that one NHL player's birth does not affect another one. Now, could you go ahead and say 10 times 80 is equal to 800? Reasonable to assume more than 800 NHL hockey players in 2009-2010 season. Now I'm going to pause on that one right there. And this is where I'd be careful. This question they created for this lesson, good question, because we can get the data for it. I also went on the internet, and I went on the internet and said, okay, how many NHL teams were in the league, like, you know, during the year 2009, 2010? All right. There were, I believe it was 30 teams. Okay. Then I thought about it and I said, okay, I did a search saying, what is the average roster size for an NHL team in that year? It said 18 to 23. So now we look at, okay, let's say 23. What's 23 times 30? It's like 690, isn't it? Which is less than 800. All right. So here we would stop because we didn't meet independence. All right. We're going to keep on going, but doing some research, I'm like, well, technically, when they created this problem, you know, they probably shouldn't have gone that big of a sample size of 80 NHL players because there's not more than 800 in the league that year. You know, they should have done something smaller than 80. They should, you know, because to make sure they stayed with the independence. You know, now if they just said professional hockey players, now that opens it up to not only just the NHL, but also some of the other leagues that are out there. But they try to stay NHL because that's where most Canadians and Americans go to play. They, you know, there are some Canadians who go overseas and play, but mainly they play in the NHL. So that's why they're trying to stick with that. So to me, when they created it, it was a great idea, but again, it made it tough. So now let's go ahead and do our chi-square goodness of fits. So in our stage here, we met the conditions, and so now our chi-squared, we would go through and say, all right, it is 32 minus 20 squared over 20, plus the next one was 20 minus 20 squared over 20. And this one's not bad to do all four of them because there's only four, so we might as well do them all. 16 minus 20 squared over 20, plus the last category was 12 minus 20 squared over 20. So there's my process. If we did all the math, that comes out to be 11.2 is what that compares to be. So I'm going to do a chi-squared goodness of fits. So I'm going to do a chi-squared CDF. What's the probability that my chi-squared is greater than 11.2? That's what I'm trying to figure out. So my lower bound is 11.2. My upper bound is something really big. And my degrees of freedom. How many categories we have? Yeah, 4 quarters. So that means my degrees of freedom would be 3. All right, so let's go in here. Boop. And nope, I don't want to do that. I want to do second vars chi-squared CDF 11.2. Leave that alone. Change that to a 3. I didn't get out of the table mode. Daggone it. Hate it when I do that. At least it saved my information. There we go. So we get our chi probability is 0.0107. And again, as we compare that to our alpha, as we compare it to a 0.05, we know we're less than. So since our alpha, our p-value is less than 0.05, we reject the null hypothesis. We do have convincing evidence that at least one of the proportions of people born in each quarter of the year in the NHL is equal throughout the year. Now, the part B, we concluded that the birthdays of NHL players were not uniformly distributed throughout the year. However, Gladwell claimed wasn't just that the distribution wasn't uniform. He specifically claimed the NHL players are more likely to be born, or the ones that are more likely to be born early in the year, is what it's claiming. Use this value to, as components. So as we look at you know, um, I didn't show you the answer to each of those fractions there. So when we look at the first quarter, second quarter, third quarter, and fourth quarter, here are the individual components. First quarter was 7.2. Second quarter was 0. There's no difference. The third quarter contribution was 0.8. And the third quarter was 3.2. So when we look at that 7.2, the first quarter has the largest component. Of the chi-squared, the chi-squared statistic. Because of having a higher value than expected. Because remember, we expected it to be even at 20 each thing, and it ended up being 30-something. So that it was a lot higher there. The fourth quarter has the second largest component. It was the second largest. And that was because it was a lot lower than expected. So that kind of supports his claim about the ones being born earlier in the year and so forth. Now, doing the test on the calculator, let's take a look at what the chi-squared goodness of fit test looks like. Chi-squared goodness of fit test. Let's see what that looks like in the remaining part of class. Let's see what the calculator feature looks like. So we're going to use that as we do some stuff tomorrow. So stat, over to test. It's on the next page. Option D says golf. Remember, in tomorrow's lesson when we do the homogeneity and the association / independence, that's the option C. So when we do a chi-square goodness of fit, notice it once where it's asking us to pull the data from. It's straight from our lists. It's doing the observed and the expected. We get to type in the degrees of freedom. So I can type in, I have them in, I don't have them in L1 and L2, but I can put them there real fast. If I go through and say, let's clear that out, because that way you can see that control to show you where the the differences are of each fraction. So let's go through and type those in real fast. He said 32, 20, 16, and 12. And then it was 20, 20, 20. And then, so it was 20. Oh, what?
25.
No, expected counts, not 25%.
Oh, right.
Because it was 25% times 80, so that'd be 20. So we want to use these numbers right there for L2. And so I'm going to go stat, back over to chi-square goodness of fit. That's not the category I want. There we go. I got L1, L2, and we said our degrees of freedom was 3. And then there is, again, when we look at our chi-squared, there's our numbers. We got that for our fraction for our chi-squared statistic. Doing the chi-squared CDF, we did get that p-value. And then notice that bottom column, the bottom row there says CNTB. So, and that's the 7.2, the 0, the 0.8, and the 3.2 that I wrote down. That's where they came from. It's in that. It shows it right there in that line.
Do you know what that abbreviation stands
contributor. I don't know. I thought that came out pretty good.
So,
This stuff.
for a particular test and then the FRQ portion of it, can we do this specific step in the do section and write it out, kind of how we did the last couple of sections? Or do we,
I would show the fractions.
okay,
I would show a couple of the fractions, get it started, and then do dot, 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 like plus dot, 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 plus the last fraction, okay? Would it be okay to do the first fraction, then plus dot, 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 plus the last fraction? Sure. That probably wouldn't matter. They just wanna know, you know, do you know how to do it by hand? Do you know what it's made up of? And stuff is taking the sum of these things there, okay? So that's why you don't have to write down every single one of the fractions. It's like, hey, just show what it gets started. It's kind of like a common courtesy, is what it is. And you know. All right.